Chapter 6, Introduction to Continuous Probability Distributions. In this video, we'll be learning about the exponential probability distribution. In section 6.2, there are two other continuous probability distributions in the textbook: the uniform probability distribution and the exponential probability distribution. While we're not learning how to do the uniform probability distribution, it is useful to know what it is and where you might see it. The uniform probability distribution is used when we don't have very much information, and so we can assume that the probability of any interval or range of continuous random variables is the same for any other interval or range of the same width. In other words, we assume all the variables have the same chance of occurring. So for the exponential probability distribution, which we will focus on, this is used to measure the time that elapses between two occurrences of an event. So, for instance, we might want to know the time between hits on a web page, or the time between arrivals of customers at a bank drive-in teller window, or the time between failures of an electronic component. All of these can impact business decision making. Like, is our web page getting enough hits frequently enough? Do we have enough tellers for all the arrivals of customers to the window? And is the time in between failures a long time or a short time, and something needs to be fixed in a particular component? So the exponential density function, as you see here, takes our continuous random variable that's exponentially distributed, and we have our statement of f of x equals, and here's some Greek letters, our lambda times e, which is our natural log, minus lambda times x. And this assumes that x is greater or equal to 0, because you can't have negative time, right? So x is always going to be 0 or more. Note that the standard deviation of any exponential distribution is the same as its mean. Fortunately, we don't have to worry about this formula, but I just wanted to introduce it to you so that you are aware it exists. One more thing to note is that 1 over lambda is the mean time between events. This is really important to remember because you're going to need it when we're working in Excel. So for our exponential probability, this is the probability that a value will fall within an interval, is the area under the graph between 2 points of that particular interval. So this formula is useful because we can actually find the exponential probability with a simple calculator. And so this is the probability that our x is between 0 and some value of interest, say between 0 and 10 minutes, or 0 and 3 hours. The formula then is 1 minus e, our natural log, raised to the power of negative lambda times our a, or our value of interest. So what does the exponential distribution look like? I like to describe it kind of like a ramp where it's higher on this end and then it drops down going low. And so depending where your mean is, which in turn impacts your lambda, because your mean is the same as saying 1 over lambda, that will tell us the height and the shape of our exponential distribution. Excel gives us the cumulative probability from left to right. You're going to hear this over and over. For all our distributions, Excel is pretty consistent. Whenever we use our Excel functions to find a probability distribution, it reads from left to right.
So let's look at an example from the homework. Problem 43. According to a website, the average cost of a stay in a hospital for a particular region was $13,000. Assume that this cost is exponentially distributed. So you can see right in the story, it tells you we're doing exponential distribution. The first step you want to do is to figure out your lambda. So here's the word lambda. That's that the symbol looks like an upside down Y. So all that you're going to do is you're going to take 1 divided by the mean. So you have to look at the story. Where is our mean? It's right here. Because in the story, while it doesn't use the word mean, it did say the average cost. So average is the same as mean. And so for our lambda, there's my upside down Y, I'm going to take 1 divided by 13,000. That's it. That's my lambda. And then in part A, it asks, determine the probability that a randomly selected patient stay in a hospital in this region will cost more than $13,400. So what's the value of interest, or the thing we're solving for, That's going to be our x, and that comes from the question. We're solving for more than 13,400. So there's my x that I need to know. And just to make sure we know how to set it up, we're writing as a probability. We're curious about x dollars being greater or equal to 13,400. Now, if we take a quick look at the Excel file, I've got my exponential distribution here, and we have three formulas we could choose from. This one, exponent.dist, is when we're doing less than scenarios. Whenever we're doing a greater than, it's 1 minus. And if you're doing between two x's, you get to do the exponent.dist twice and then subtract them from each other. So you can see the example from the video. That's what's the probability that a randomly selected patient's stay in a hospital will cost more than 13,400. Since it's a more scenario, we're going to be using the formula that says 1 minus exponential distribution. There's my 1 minus exponent.dist, and we got to put in our variables. We first put in the x. So recall the x I'm interested in solving for. That's my 13,400. Then we're going to put in our lambda. So that's what we found up here. And what I recommend is just leaving it in fraction format because it is going to be such a tiny decimal. Let Excel do the math. So you can just do 1 over 13,000 for your lambda. And then, of course, it's going to be true because it is cumulative. We are adding up the area under the curve. So then you're going to enter all of this into Excel, and we'll get 0.3567. Let's continue on. Same problem, still same hospital, same region. And you'll notice we want to make sure we know what our lambda is. It hasn't changed. So our lambda is still going to be 1 over 13,000. Okay, so don't change it just because we're doing another part of a problem. Now in part B, we want to calculate the probability that a randomly selected patient's stay in a hospital in this region will cost less than 8,100. Let's go ahead and make sure we know what our value of interest, or x, is. That's going to be the 8,100. That's what I'm curious about. And we're curious about less than 8,100. So again, now I know which formula to use in Excel, which is going to be this one right here. I just have to plug in my x of 8,100. My lambda, which has not changed, it's still 1 over 13,000. And again, you're like, where's the 13,000 come from? That's that average cost from our story, and then true. And then when you hit enter, after typing all that into Excel, we get 0.4637. And that's how we do the exponential distribution.
So in other words, we've covered in Chapter 5 the binomial distribution and the Poisson distribution. We did not study the hypergeometric. And these are all random variables based on counting. And then in this chapter, Chapter 6, we learned about the normal distribution and the exponential distribution and how to use them. And we touched on the existence of the uniform distribution. And these are used when our random variables are uncountable and are determined by measuring. So if you have any questions, just let me know.